Hello everybody, how are you today? Today we're going to look at Fourier Transform. Okay, Fourier Transform is also denoted by ft and is defined in the infinite interval. Okay, so we want to look at the definition. The definition of Fourier Transform is given by f hat omega equals to minus infinity to infinity fx e negative I omega x dx. Okay, in another word, Fourier big capital F Fourier transform of fx is given by f hat omega. Okay, this is the definition for Fourier transform. Now, I want to show that this Fourier transform of f a plus ax plus b, Fourier transform of f ax plus b equals to 1 over a eib omega over a f at omega over a. Okay, we want to show this. Okay, to show this, we need to use the definition. Okay, by the definition, we have f hat omega equals to minus infinity to infinity fx e negative I omega x dx. Now, this is our fx. Okay, this whole thing is my f hat omega. Okay, so putting fx into here will give me minus infinity to infinity f of ax plus b e negative I omega x dx. Okay, now the next step will be to solve this. Okay, how to solve this? Before we do this, for simplicity, we will say let y equals to ax plus b. So we have here ax equals to y minus b, x equals to y minus b over a, and here you differentiate with respect to x. So dy dx equals to a dy over a equals to the x. Okay, once you've done that, you're gonna put it into this integral. So we have f hat omega equals to minus infinity to infinity f of y, this become my y, e negative I omega, and my x will be y minus b over a, and dx will be dy over a. Okay, now what's the constant here? 1 over a is a constant, fy, and I can split this integral into e negative I omega y over a, minus minus will be positive, e I omega b over a. Okay, d omega, dy. Okay, are you with me? So what happened here? So you just split the integral e negative I omega y over a for this one, and negative will be positive, e I omega b over a. So in other words, I have this one, e alpha beta plus b plus c. So how do you write this? You have e alpha b e alpha c. Okay, this is what happened here. Okay, so what happened here now? This is nothing to do with y, so I can bring it as a constant. So I have 1 over a ei omega b over a. Okay, now we have from minus infinity to infinity f of y, ei omega negative I omega y over a dy. If you look at this integral, this is similar to the definition, because the definition of Fourier transform from minus infinity to infinity f of x. Okay, let's write the definition. Minus infinity infinity f of x e negative I omega x dx. This is the definition of Fourier transform. Okay, so if you look at here now, the difference is this one. Now we have omega over a. If this is known as half hat omega, so you will have 1 over a e I omega b over a f at omega over a. So I have shown you the Fourier of f ax plus b equals to one over a ei omega b over a, and so on. Okay, so this is by definition. Now let's look at one example on how to use this formula. Okay, the example will be, find the Fourier transform of fx equals to 5e negative x plus 2. Okay, so this is the example. Now we know f of Fourier of a plus ax, Fourier of ax plus b is equals to 1 over a ei b omega over a f at omega over a. So we need to use this. Okay, so first of all, how do you do this? So we have Fourier of 5e negative x plus 2. Now by the linearity property, I can take 5 out, leave me with Fourier of e negative x plus 2. Okay, now my function, my f function here has x plus 2. Okay, that's another thing. Okay, we have x plus 2. So what happened here? Now we're gonna find it f of Fourier of f of x plus 2. Okay, so what do you have? My a is 1, my b is 2, so that will give me 1 over 1 e, I'm using this formula, I, b is 2, omega over 1 f hat omega. So I have e I 2 omega f at omega. Okay, so now this will leave me to, so what I have here, so what is my f hat omega? My f hat omega now will be this part here will be the Fourier of e minus x, modulus of minus x. Okay, so we have evaluated this part here. Now all we left with this, and this is by the definition, by the Fourier table. Okay, table, Fourier of e negative modulus x is given by I think the definition is given by this. If I'm not mistaken, it should be minus a modulus x is given by 2a over omega squared plus a squared. Okay, so in my case, my a is 1. So Fourier transform of e negative modulus x is given by 2 over omega squared plus 1, because a equals to 1. Therefore, now my final solution, what we do here, we want to find, the question asks you to find Fourier of 5e negative x plus 2. Now putting all the pieces back, we have earlier on 5 e2i omega Fourier of e negative x, which is 5 e2i omega, this one, 2 over omega squared plus 1. Okay, therefore your answer will be 5 times 2 is 10 e2i omega over omega squared plus 1. Okay, so this is the Fourier transform using the property of this one. Okay, so the Fourier transform, if you are given a Fourier transform of a function different than the given in the table, so we have to use this definition. Okay, and all you need to do is you have to transform this first, make it as the original as the table. Okay, and to transform this, you need to use the Fourier transform of f ax plus b equals to 1 over a, and so on. And then whatever left now this can be found from the table. Okay, this is given from the table. Okay, and then you put back into the equation. Okay, 1 over x squared plus x plus 1. Okay, so how to find this? So this is what we got to do. Now we know by the Fourier transform definition, or from the Fourier transform table, f of 1 over x squared plus a squared is given by pi over a e negative a omega. Okay, so this is the closest from the table that we can use. Okay, although this is not quite look at that, we need to change that. So the first step we need to do is to change this by completing square. Okay, we know that by completing square, x squared plus x plus 1. What do we get? We have x squared plus x equals to minus 1. Now this is 1, so we have 1 over 2 squared minus 1 plus 1 over 2 squared. Okay, now simplifying, now this will give me x plus half squared equals to negative 3 over 4 from here. So we have x plus half squared plus 3 over 4. Okay, so we have close to that. We have close to that now. This is my x squared. Okay, so what we have here, we have next step we want to do is we want to find the Fourier of 1 over x squared plus my a, this is my x, the whole thing, this is my a squared. Okay, So if a squared is 3 over 4, my a is plus minus square root 3 over 2. Okay, so I'm gonna write this as square root 3 over 2. Okay, so by the definition, what we should get, using this definition now, we have pi over square root 3 over 2 e negative square root 3 over 2 omega. Okay, I hope you're with me. Now, if you look at that, now we need to use a translation, Fourier Translation formula to change this one, because we have x plus half, not x squared. Okay, so what you do here, we know the Fourier of f a plus b, f a x plus b is given by 1 over a e I b omega over a f at omega over a. Okay, now what we want to find is our Fourier of f of x plus half. Okay, so that means my a is 1, my b is half. This will give me 1, okay, 1 over 1 a I b over 2 omega. Okay, b is half, so 1 over 2, so give me I omega over 2 f hat omega over 1, so which is e I omega over 2 f at omega. Okay, now what is f hat omega? Okay, f hat omega is the one we have obtained here. So Fourier transform of this will give me f hat omega, which is this thing. Therefore, what we have here, Fourier transform of 1 over x squared plus x plus 1 is given by e I omega over 2 f of omega, which is pi over 2 pi over square root 3 over 2 e negative square root 3 over 2 omega. Okay, so simplifying this will give me 2 pi over square root 3 e I omega over 2 e negative square root 3 over 2 omega. There you go. Okay, so this is how you solve the given question. Okay, let's look at another example. Okay, another example is similar to that, taken from your book. Okay, another example will be find the Fourier transform of 1 over omega x squared. That's x squared plus 4x plus 13. Okay, so we want to find Fourier transform. Okay, similar to the previous example. Now we want to find the completing square of by the completing square of x squared plus 4x plus 13. Now what do we have? We have x squared plus 4x plus 4 over 2 squared plus 13 minus 4 over 2 squared. So I have x squared plus 4x plus 2 squared plus 13 minus 2 squared. X plus 2 squared plus 9. Okay, this is what we obtain by completing the square. Now we know the definition of Fourier transform. The definition of Fourier transform from 1 over x squared plus a squared is given by pi over a e negative a omega. Okay, now if you look at here, we want to assume now this whole thing is my x squared, this is my a squared. Okay, so what do we had by using the definition? Fourier of 1 over x squared plus 9, sorry, it's not 9, it's 3, okay, 3 squared, which means my a is 3, I have pi over 3 e negative 3 omega. Okay, this is good. Now we need to use, now we want to change back. So what is this? This is my f hat omega. Okay, now what we want to use the translation formula. Fourier of f ax plus b is given by 1 over a e I omega b over a f at omega over a. Okay, what translation we want to make now is this one, x plus 2. So Fourier of f x plus 2, which means my a is 1, b is 2, is given by a is 1, so 1 e I omega, b is 2, 2 over 1 f at omega, a is 1. Okay, what is f hat? So f hat is whatever we are obtained here, right? So therefore I can say that Fourier transform of 1 over x squared plus 4x plus 13 is given by e I omega 2 f at omega, which is e I omega 2 pi over 3 e negative 3 omega. Okay, so you can't simplify this, but I can take out the pi over 3 term, so we have e I omega. Normally you will write like this, okay, 2i omega e minus 3 omega. Okay, that's all for today. So show you more example in my next video.